Thanks, Simon, for the introduction. So today I will present my part of my PhD work. So it's exploiting piano acoustic in automatic transcription. So my other supervisor is Matthias Moch. He's not here, but I think most of you know him. The talk will have, we first give a very brief introduction to the automatic music transcription. Then we get some background for piano acoustics, sorry for that, and MF techniques. Then the rest, the following two talks will be part of my main chapters. The first one is modeling the decay of piano tunes, then and the other one is attack decay model for piano transcription. Then we get the conclusion. So automatic music transcription is the process of converting a music signal into a symbolic representation, like a time pitching representation or like a list of note events. So what's particular for piano sounds is like he have a very large pitch range. The fundamental frequency is range from 20 Hertz to 4,000 Hertz. Then the number of simultaneous notes are also very big. It can be more than 10 notes at the same time with a sustained pedal. And the harmonicity and the decaying note energy is also related to the piano acoustic, the construction of piano. Then we will introduce later. So what's piano acoustic is about the feature related to piano physics. So the first is very well known in harmonicity, which means the partials will be stretched a little from the harmonics here. Then the other one is the excitation structure, which means when the hammer hits the strings, then it hits at a specific position, like 1/7 of the strings, then will give us a very specific excitation structure. Then there is also one other thing about the attack motion, which is percussive onset. This means this is the spectrogram of a sound. Then it will, like at the first beginning, it will be like the spectrogram is flatter, so it's like percussive onset because the attack by the hum. Then later will be like a more harmonic structure. And also the decaying, we think that because there is no energy input for after your finger press the key, so you think the energy always like decaying after that. But there are several decay patterns. Like here, there is a lot of curves here, which is what piano acoustics start. So we try to use some clues from the piano acoustic to get our transcription work better for piano music. So this part is about the technique part we used. It's based on the long-negative matrix factorization. So to build an MF-based transcription system, you have to have the time frequency representation, which is usually, I'm not sure it's clear enough. So the first one is the STFT, security, and ERB. So we use the first one. It's simple and linear, and also because we need to deal with all the partials of the sounds. The other two the partials will be very close for the other two representations. So we use the first one. Then after you have a spectrogram like this, then you can factorize it factorize it by MF into the activity and templates. So during the FT, you also have a lot of options to choose. The first one is the cost functions. So there are 3 cost functions. There are some issues about convexity and also about scaling, which you can have. This is about the chapters in my thesis, so you can have more details here. So the other thing come with the cost function together is the penalty terms. This is where you can add the constructions, constraints like sparsity, temporal continuity, and inharmonicity. Always at the same time when you choose the cost function, you can add a lot of terms after. Also, there's some basic com-used update rules that you can choose from, but it's always like a multiplicative updates for the MF and EM algorithm for the PLCA. So for these 2 parts, it's kind of like the parameter estimation problem. So you can use some like optimization method to make the cost function better. And after that, you get a time pitch representation. Then there is a very common post-processing like thresholding to make it like the binary output, and also to restrict the minimum duration of each node, and also HMM smoothing. Then after that, you will get the piano roll or note events representation, which is we try to get from the for the music transcription. So after we briefly introduce the background of the piano acoustics and the MF we used, then we are going to our main work. So the first thing is modeling the decay of piano tones. So for this work, we trying to tracking the decay shape of each partial. Then we know the one strings will, the damage of one strings will decay like exponentially. Then in the dB scale, it can be fit by a linear decay. Then we can see there are 2 different shapes. This is double decay, this is also double decay, and this is base, which means decaying with a curve. So the first double decay is caused by the coupling between the soundboard and the piano strings. Then the second 2 are caused by the coupled piano strings. So how many partials we will track? So we will track like first 30 partials below the Nyquist frequency of 88 notes in 3 dynamics. So here's how we do it. So before we track the decaying of each partial, we need to find the partials. We know this is kind of inharmonicity of the partials. So this is fundamental frequency. This is the frequency for the nth partial. So it will be stressed by this inharmonicity factor B. So when you estimated piano sounds, the pitch and the inharmonicity factor will be estimated jointly by considering all the partials. So this work was an existing method by Riga in his PhD work, so we don't give the details about that. So after the method, we get all the partial frequency like this. And this is what the smooth B factor, inharmonicity factor for all the piano notes from MIDI index 21 to 108. So after find all the partials, we can get ready to track the decay pattern. So there is 3 models we use. The first one is, of course, linear regression, the multiple phase regression, and nonlinear curve fitting. So there are some examples of what fitting did, and this is our project function. These 2 are quite easy. It's just the lines. Then for this one, we have to get a good initialization for all these parameters. So the first AT plus B will be initialized by the linear regression results. Then capital A is the amplitude for the beating. So this is theoretical value is 40. Then this beating frequency is initialized by the interval between the 2 values, or we can see if it's just 1 value here, then we see this is half of the interval of this value. So this is how we initialize it. So get some examples how they fit. So we after we fit all the partials, we try to compare the linear model and the fixed model. The linear model is we track each partial by the linear regression. Then the mixed model, which means we use the best result of these 3 models. This is the flow chart for the process. Then we use the R square to indicate how good the fitting is. So this result is like the better, then the fitting is better. The bigger the fitting is better. So here is the result. So this is for T, the dynamics means the loud sounds. Then we have 572 partials. We track like this, how many partials like this. Then we can see for all different dynamics, we get the mixed model get better fitting, about 50 percentage points, and also the fitting is better for the loud sounds, and because I think when the sound is quiet, then you have less data to estimate, so your result will be less stable. Then we group adjacent 11 notes into one group, so we have 8 groups for all the piano sounds. We find the biggest improvement is at group 2, because for the notes in group 2, most of them have 2 strings. Then the beating is quite intensive for the notes here. So we think the mixed model get the biggest improvement for these notes. Then we also try to draw some conclusion about the decay response and the decay of different dynamics. So for this is all the decays of all the partials. Then the X is the partial frequency. So this means all the frequency here maybe not come from the same note. They're just the partials of the same frequency. The gray scale indicates the pitch index. So the darker the pitch is lower, then the lighter, then the pitch is higher. So we can see what partial decay, how to say, is like if you have the higher frequency, you tend to decay quicker, faster, but there's still quite a large variety of the decay rate. So we can see you cannot model the piano decay by one filter. Maybe you can model the decay of each note by one per filter, but to model the decay of piano by one filter maybe not work that well. So for the second part, we're trying to understand how the dynamics works on influence on the decay rate. So we just plot all the first partial, the first 5 partials. Then we see for the low, no. So for the high pitches, there is a little noise, but for the low pitches and the middle pitches, then the decay rate quite identical. So we can draw the conclusion that the decay, the dynamics doesn't give significant influence on the decay rate. So we think for the notes played by different dynamics, we can model them by the same decay rate. So after we get all this, trying to study the piano decays, then we try to use this method, trying to use these knowledges to propose an attack decay model for piano transcription. So, of course, the proposed method is based on MF, then with 3 refinements. The first one is introduction of the attack and harmonic decay components. So we will previously say the attack part is more percussive. So we separately model these 2 parts. Then the second part is use a shape, a spike shape note activation that's shared by these 2 components. Then the third part is modeling the harmonic decay by exponentially decaying function. So here is our model. 2 parts, the attack part and the decay part. Then so for the templates for these 2 is kind of like this. We will come to this later. Then for the attack activation is this is the note activation and this is attack activation. So this is kind of a confluence between the note activation and the attack envelope. Then the decaying activation is just like this. We assume it decays forever and it decays exponentially. Then this is the whole system. Then this is one example of our results. It's a simple piece. So this is the attack activation. So we can see we can get onset by the attack activation. And for the decay activation, not sure it's clear enough. So if it's start 1 point, then it's just decaying forever to the end. So in this case, we cannot directly to find offsets. We have some methods adapted from Sebastian's method. Later we will come to. So this is our results. We think it's quite close to the ground truth. So for the onset detection, we work on the attack. We work on the attack activation, so it's like just like a very normal onset detection method. We get the picking first by thresholding and smoothing. Then we find that this is just 1 note, but you have two onsets. So we merge some very close onset, but later we think we can use just a difference function to tackle this problem. And for offset detection, we first calculate the cost of state off and on for each pitch. So for state on, it's just the reconstruction between the spectrogram and the reconstruction. And the state off is the spectrogram and the reconstruction without that pitch. So after we calculate that, we normalize the two states, so we can clearly find this is on stage, on stage, on stage, on stage, and here. So we segment the whole pieces by the detect onset. So for each segment, we try to find offset by applying dynamic programming, but we also trying to just smooth this normalized cost. They also give us very similar results. So maybe later we'll use just some thresholding on the normalized cost, because it's already very clear where the pitch is, where the note is. Here, so before we doing the transcription, we train the templates and train the transit pattern for each isolated note. The first note, for first round, we just set the activation based on ground truth. Then we update all other parameters. Then we get all the transit patterns for 88 nodes. Then we want it less. We want to reduce the number of the parameters, and also we want to reduce the potential of overfitting. So we use the average transit pattern. Then so for the round 2, we set the transit pattern by these results, and also H is also initialized by the ground truth, then update all other parameters. So we compare our results with a 3 state-of-art method. So for the first 2 datasets is come from the MAPS dataset. We get all the best results. We have to say this one is so our method and the Emmanuel's method are the supervised method, and this one is unsupervised method. So we just trying to see how much better we can get if we know the notes of the piano. So for the first 2 datasets, we get the best, all the results is best. But for this one, our note onsets, our note level results are not that good. We think this is because this dataset is from a piano competition. There is a lot of short notes, so we think this is because our assumption of exponentially decay, which because it have a smooth activation, but it can have no interruption by other notes, by notes of other pitches. But by this method, we can not estimate the note offsets. So this may be the reason why we didn't get quite well for this data set. Okay, it's almost finished. So we for this work, we propose a state-of-the-art piano-specific transcription system by explicitly modeling piano acoustics. And we can see the model can be understood as a deconvolution method, because with a patch parameterized by 2 sets of templates and activations. So this allows us to build a node-level system. So in the future, we assume the energy of node decaying exponentially, but for the work we started before, we know that each partial decay differently. So we want to model the decay rate by a decay filter to get better modeling of the piano note, and also trying to find a way to estimate node offset more accurately. In today's work, I introduced 2 parts of two main chapters of my thesis work. So first, model the decay of piano tunes, then present and propose an attack decay model for piano transcription. So we show that piano transcription performance can be improved by explicitly modeling piano acoustic features. Okay, thank you.